Okay, in this video, we're going to look at question 7, and part A says, find the Maclaurin series for the function arctangent of x and an interval on which your series converges. Okay, so now just like in the last example when we were looking at the natural log of 1 plus x, the key observation here is that the derivative of the arctangent of x is equal to 1 over 1 plus x squared. And see, this expression is of the form a over 1 minus r. See, I can write it as 1 over 1 minus a negative x squared. Okay, so I can expand this expression then into a geometric series by taking a to be 1 and r to be negative x squared, right? So I get a, the first term, and then to get to the next term, you just multiply by the common ratio, negative x squared, so that gives us a negative x squared. Multiply again, you get positive x to the fourth, minus x to the sixth, so on and so forth. Okay, and we have equality here provided the common ratio r, which is negative x squared, is strictly less than 1 in absolute value. Okay, so note that this condition on x is equivalent to saying that the absolute value of x squared is strictly less than 1. I can drop the negative because of the absolute value. And now taking square roots, right, I get that the absolute value of x is strictly less than 1. Okay, so all together then, we're saying that the derivative of the arctangent of x is equal to this series, 1 minus x squared plus x to the fourth minus x to the sixth, and so on, right? And we have equality here for all x in this interval that I've shaded in blue. All right, cool. So now just like the last example, right, if we want a series representation for the arctangent of x, I want to undo this derivative. And so I'm going to integrate term by term. Okay, so the arctangent of x will be the integral of this series. So integrating term by term will give us x minus x cubed over 3 plus x to the fifth over 5 minus x to the 7 over 7, so on and so forth. And here I've included my constant of integration, right, my plus c. And now it does turn out, we're not going to be able to prove this. It goes a little bit beyond what we're doing in this class, but it is true that this series does converge to the arctangent of x at both of these endpoints, right? So at x equals negative 1 and at positive 1. All right, cool. So now let's go ahead and evaluate the constant c. Okay, and I'll go ahead and plug in x equals 0, just like we did in the last example. So on the left, I have arctan of 0. And on the right, I have this string of zeros and then my plus c. And so recalling that the arctan of 0 is equal to 0, this implies that c is equal to 0. Okay, so we record all of this as follows. Okay, the arctangent of x is equal to this series x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, and so on. Okay, and this series converges to the arctangent of x for all x in the interval from negative 1 to 1 inclusive. Okay, now I can write this series using sigma notation. Here I'm summing negative 1 to the n, right? That gives me the sign alternation. And note I'm starting the index here at n equals 0. And now for the denominators, these are the positive odd integers, right? 1, 3, 5, 7, and so on. So I need a 2n plus 1 down here. And then the exponents, those are also the positive odd integers, 1, 3, 5, 7, and so on. So I have a 2n plus 1 up there. All right, now for part B, it says, it turns out that the series you derived in part A converges to the arctangent of x at x equals plus or minus 1 as well. That's what we're saying up here. What happens if you plug in x equals 1 into your series? And then down below, I make this little footnote. Just says a bit about the history of the result we're about to write down. All right, so if we plug in 1 for x, on the left we get the arctangent of 1, and on the right we get 1 minus a third plus a fifth minus a seventh, and so on. And if you recall that the arctangent of 1 is pi over 4, we get this rather remarkable identity that says pi over 4 is 1 minus a third plus a fifth minus a seventh, and so on. Okay, so this result goes way back. It was, as far as anyone knows, first discovered in 14th century India by a mathematician named Madhava, and then it was rediscovered about 300 years later in 17th century England by a guy named James Gregory. Okay, and I think one of the things that makes it remarkable is that this number pi, right? I mean, this is a number that captures people's imaginations, right? It's equal to the ratio of the circumference of a circle to its diameter. Okay, but what this identity is saying is that we can generate the number pi. Note if I multiply both sides by 4, I get that pi is equal to 4 times this rather easy to describe series, right? Where I'm adding up the reciprocals of the positive odd integers, and then I have this sign change, okay? Now, the downside is that you have to add up lots and lots of terms of this series before you start getting good approximations to pi. You might want to play around with your calculator to do this. So the convergence is really slow, in other words. But in any event, rather cool, and that's a good place to stop. All right, I'll see you in the next video.